If I was going to write the chemical formula for calcium bromide, let's try that. What would be the chemical formula for calcium bromide? Okay, let's do a quick review on how we find the chemical formula. First of all, it's an ionic formula, isn't it? Because it has a metal and a nonmetal, or a cation and an anion. We need to locate calcium, which we know is a what charge? +2. And bromide is way on the other side. It is a -1. So when I put these together, do you know how they're going to go together? How's it going to be? Ca2Br, is that how it's going to go? No, it won't work like that, okay? So I need how many bromines to cancel out that calcium? I need 2 bromines. So I only need 1 calcium and I need 2 bromines, right? I can see that by my charge. I need this to be -2. So in order to cancel out my +2, and in order to get -2, I would need another Br -1. Okay, do you remember the other method I taught you? What did we call it? What did we call that one? We called it the crisscross method, right? So we crisscross that down from a charge to a subscript. And there's a 1 right there, but if there's a 1 subscript, you know what we can do? We can just leave it off, right? We just leave it off, okay? All right. Try this one. Let's try aluminum phosphide. Aluminum phosphide. If this is Al +3 and phosphide is -3, what if I didn't notice and what if I did the crisscross and it was Al3P3? What would I do then? Reduce them down to be AlP. That is my formula. Do I have any charges in my final formula? I don't, nor should I ever. I should not ever have charges in my final formula. What does the charge of my final formula need to be? Neutral or 0. Good. Okay, do we have any questions about those binary ionic compounds before we move on? Okay, we're gonna take it up a notch now. We're gonna talk about these ones in the middle. Do you see these guys in the middle that have multiple charges listed? Okay. It only happens with which set of compounds, or with which set? Or does it happen with metals or non-metals? Metals. Only metals, right? Anions or non-metals, they never have this issue, but the cations have an issue where they can take on multiple charges. Means they are able to give away a couple different electrons, right? They like to maybe give away 2 or maybe give away 3, right? But these are the most common charges listed here. So next to it is a Roman numeral. That Roman numeral tells us the charge of that particular compound. So if I see one that's written like this, cobalt 2 oxide, that tells me, this Roman numeral tells me which version of cobalt I am dealing with. Okay, it tells me the version of cobalt I need to use. It also tells me directly the charge of cobalt. Okay, so when I go to make the formula, I would say cobalt is a +2 and oxide is a -2. And so what's my finished formula there? What would it be? Okay, I want my chemical formula. What is it? COO, right? It goes together 1 to 1, don't they? Because we see these charges would cancel each other out. Okay, the Roman numeral has to be included in that written name. Okay, so if you ever have an element like cobalt that has a Roman numeral, we have to include it in its written name. It's really important. When it's there, then we know that's the charge of that particular cation. Okay, let's try another one here. let's try chromium 3. Chromium 3 sulfide. Chromium 3 sulfide. So chromium is number 24, okay? And so chromium is Cr. And what's its charge? +3. It tells me right from the Roman numeral. And sulfide never changes its charge. It's a -2. So do you guys prefer the crisscross method, or do you prefer to work it out with the charges? Do you have a preference? Okay, so let's just do crisscross. Okay, and that means it would be Cr2s3. Agreed? Yeah. Cr2s3. And then if you want to check yourself, we know that chromium is +3, and there's 2 of them, which gives me +6. Sulfide is -2, and there's 3 of them, which gives me -6. So we see that they're neutral, right? We can always check ourselves after we've built our formula. Might be a good idea. Okay, but this right here is our final formula, not with charges left. Okay, I'm telling you that multiple times because it happens every single year. I get formulas on the test that say Cr2 -3, S3 minus whatever. I get, this is what my formula looks like. No, we can't have charges in our final formula. Okay, let's work backwards now. Now I'm going to give you the formula and you give me the formal name. Okay, I want to do this one, MnO. MnO. Mn is number 25. Nope, not quite. Look at the, does manganese have a Roman numeral next to it? So we need to figure out which version of manganese is it. Good. It is manganese 2 oxide. And the Roman numeral gets like just like that in the middle and a parentheses around it. How did we know it was manganese 2?
Because oxide is negative.
Exactly. It fits right with oxide, which is a -2. Okay, I want you to look at this real quick. What if, what do we assume is right there? We know they're 1s, right? So if we reverse the crisscross, that would leave us with Mn +1 and O -1. That's not true, right? Because oxygen is not a -1. It's a -2. So to fit together, they have to be a +2 and a -2. Okay, so this would be our written name, and then MnO was our formula that we started from. Okay, let's try this one. How about this? I want you to write out the full written name. Okay, I'm going to give you a couple minutes here to write out the full written name. You need to find Sn, which is number 50. So we know it's going to be tin sulfide. Agreed? Does it need a Roman numeral?
Yes.
Yes. And what is the Roman numeral? I don't think it's 2. So let's figure out why. I actually think it is. Nope, you're right. It is 2. Nope. You're right. It is 2. Okay, we knew it because they fit together 1 to 1, didn't they? Okay, very good. Nope, you're exactly right. Tin 2 sulfide. Did everyone else agree with that? Okay. I meant to make that problem more complicated and then I messed up the actual formula. So you guys are right. Let's try another one. Let's try PD2. No, PDO2. All right, try that one. Palladium 4 oxide. I agree. Did we all get the 4 as the Roman numeral? Okay, very good. Okay, you guys are pros. Okay, usually it takes a little bit longer to see that reducing part of it. But we know it's a 4 because oxide is always -2, and there's 2 of them. So this has to be +4 to even that out. Okay, very good. Okay, I love it. Let's keep moving. We're going to actually look at something with polyatomic ions. What do you think that means? Polyatomic ions. What does polyatomic mean? Multiple, many, right? So it is an ion that has multiple atoms in it. It's not just sulfide or oxide or calcium or whatever. But it's an ion that is like basically a compound. It's a compound that's an ion. And look up here in your box, right up here. You see this box? Those are all a list of really common polyatomic ions. I'm going to ask you eventually to memorize a few of these, but today we're just going to learn how we can add these into our ionic compounds. What's the charge of most of our polyatomic ions? Are they positives or negatives? Most of them are negatives, right? So they're almost always going to go in as the anion. There's a couple exceptions, ammonium and hydronium, they're on the bottom there, but most of them are negatives. Now, the rules with naming polyatomic ions is that they just keep their regular name. They get to keep their regular name. So I want you to, let's just look at and find phosphate. Find phosphate in the box. That's where all the polyatomic ions will be, and they're listed alphabetically. Do you see phosphate?
Yes.
It is PO4 -3. Okay, what I need you to understand about phosphate is that this formula, PO4, that is its identity. It can never be altered, right? You know how we talked about reducing things down? This 4 never gets to be reduced because it is part of phosphate's identity. So we don't ever mess with a polyatomic ions formula. That kind of makes sense? Okay, so let's look at one here. So let's try calcium sulfate. Calcium sulfate. Right? Cation, and then the polyatomic ion gets to keep its regular ending. So calcium is a +2. And what's sulfate? SO4 -2. -2. So how will these fit together? How will they fit together? Nope. The 4 stays. The SO4 is its identity. So SO4 never gets separated. It stays together. It's like you're just working with S, right? That is the formula. So it fits together 1 to 1 because this one is a -2 and a +2. So my final formula is just CaSO4. That's it. They just fit together. We don't alter sulfate at all, right? It stays SO4 because if we do change it, it's not sulfate anymore. Okay? Okay, how about lithium carbonate? Lithium carbonate. Let's find lithium's charge. It's +1. Did you find carbonate yet? CO3, and what is carbonate's charge? -2. Do we see how they're going to fit together? Okay, or you can use the crisscross. It becomes what?
Li2CO3.
Perfect. Li2CO3. Okay, if we did our crisscross, it would just be that we ignore the plus and the minus, we bring the 2 down, and we bring the 1 down. So it's like there's a 1 right out here outside of carbonate. Okay, but we don't have to include that because it's a 1. Okay? All right, we're going to keep ramping them up a little bit. Let's try magnesium phosphate. Magnesium phosphate. Not manganese, magnesium. Magnesium is a plus what? Okay. What was your? Nope. All right, and what's phosphate? PO4 minus 3. Okay, so let's do crisscross here. We bring the 3 down, and we bring a 2 down, right? The 2 comes down here, the 3 comes down here. So it becomes Mg3, and then PO4, and we need 2 phosphates, don't we? So we put parentheses around the phosphate, and the 2 goes on the outside of those parentheses. Okay? We use parentheses around a polyatomic ion anytime we need more than one of that polyatomic ion. Anytime we need more than one of a polyatomic ion, you use parentheses. So I think that might be worth writing on our slide. Anytime we need more than one of a polyatomic ion, we use parentheses. Okay, you'll notice up here with carbonate, we only needed 1 carbonate molecule. So we did not have to use parentheses. But down here, to make it neutral, we needed 2 of the phosphates, 2 of the PO4s. So we had to use parentheses. Okay. All right, let's keep going. Let's try 10 for oxalate. 10 for oxalate. And we see an ATE at the ending. That's a good indication that it's coming from our box of polyatomic ions. Oxalate is not on the periodic table itself. It's in the box of polyatomic ions. Okay, so let's write it out. 10 is SN and it's plus 4. Did you find oxalate? C2O4 minus 2, right? I want you to notice right off the bat, we don't reduce these because it's part of its identity, right? It's not, we're not changing anything there. But we need to fit these together, don't we? So we're going to bring the 2 down and the 4 down, and it becomes SN2, C2O4, 4. Okay, now what do we see? Can it be reduced? It can, right? The only things that can be reduced are this one and this one, right? So our finished product here will be SNC2O4, 2. Okay, this 2 applies to this oxalate molecule, right? There are 2 of that in order to cancel out my tin cation. Okay, questions there? Okay, I'm going to give you a few of them. Some of them I'll give you the written name. Some of them I'll give you the formula, and you're going to give me the opposite. Okay, so we're just doing lots of practice here. I don't know if we're practice, but sorry if you're running out of room. You can just use your extra space on your slides. Okay, let's try. Oops. Okay, that one you're going to give me the name. That one you're going to give me the name. That one you're going to give me the formula. And the last one, you're gonna give me the formula. So I've got 4 questions here for you. You're gonna give me the written name on the first 2 and the formula on the second 2. AG3PO4. Raise your hand if you think you would like to volunteer your answer for that. AG3PO4. All right, Peter, what do you got?
Silver phosphate.
Silver phosphate. Good. Do you think it needs a Roman numeral?
No. No.
It does not. No, it doesn't. Because there's no Roman numeral listed there, right? The only time you need to include a Roman numeral is if there is multiple charges listed. So silver, Ag, doesn't have any other options for charges, so we don't have to include the Roman numeral. So we only need to include it when it's a must. Does that make sense? Not going to include it in other ones. So this was perfect. Very good. CRP. What do we think? Chromium. Oops. Chromium 3. And then what'd you say? Phosphide. Very good. How did we know it was phosphide rather than phosphate? How did we know? What's different between phosphide and phosphate? Yeah, it's not a polyatomic. It's just the element by itself, which means it has to end in IDE. Very good. Sometimes once we start working with phosphate, sulfate, carbonate, right, we kind of get into a habit of putting those things as our answer instead of just the element itself, right? We need to understand those are different things. All right, mercury 2 oxide. Agreed? Mercury is a +2, oxide's a -2. They just go together perfectly. Good. How about a last one? Riley, what'd you have? SO3 what? What'd you say? I can't hear what you're saying.
This is the one I
That's okay. That's fine. You're right so far. The only thing we're missing is how many sulfites do we need? Anybody? I think we need 3, right? So we're going to have an SO3, 3, because we're going to take AU, which we said is +3, sulfite, which is -2, and we'll crisscross, and that 3 comes outside of there, and a 2. You guys did really well with that. Good job. We're going to stop right there for today. You've got just a few minutes, believe it or not, but I don't think I'm going to send you with homework today. You've got about 5 or 6 minutes. Why don't you maybe flip through your 1 through 20 flashcards a minute or a bit, right? Whatever that might look like. But our quiz will be on Monday.
Sorry, all my head.
You already got it in your head? I love it. I love it. I love it.